Welcome, Brittany.
Hello, and welcome to my talk. My name is Brittany Bahk, and I'm here to share notes on my project, which is repurposing vulnerability tickets to predict severity levels and introduction to natural language processing and classification algorithms. Thank you. So how I got here. I started my career mostly on the receiving end of information as a tech writer, and then transitioned into InfoSec as a security analyst working on the compliance side of things. Afterwards, I moved into a hands-on role as a security engineer, where I found my niche as an operations process lead. It's this role that allowed me to work with multiple security workflows and continue to ask the question, how can we do it better? From my experience, doing something better or process improvement starts with a lot of talking. Typically, teams get together and discuss how something is supposed to go. Afterwards, there is some testing to work out issues. Once enough tests have been run and a working process is in place, then commitment in the form of documentation occurs. The documentation signals there is an agreed upon method of carrying out a process. The expectations at this point are set. Eventually, the process is completed enough times that consistency of expected input and output are generated. And then the process is automated, which simply speeds up the rate of completion. It's at this stage a lot of data is collected. There's always the possibility of going back with new information found and running through these steps again. But eventually, you start asking the next question, which is, what do we do with all this data? So in the context of this project, the data we're talking about is in the form of vulnerability tickets. Vulnerability tickets are created to track the remediation of detected vulnerabilities. They typically hold a lot of sensitive information about the impacted product or service, including associated teams, remediation instructions, published descriptions, and completed resolutions, to name a few. They are usually maintained in a repository where they can be tracked and recalled as needed. They are prioritized based on severity. They can provide descriptive statistics where the gathered information can be quantitatively described or summarized. Vulnerability tickets are generated in natural language. Natural language processing is under the artificial intelligence umbrella. Since there is not a one-to-one match between natural language and computer language, you must convert natural language into a format the computer can understand. Once this conversion is completed, then your dataset can be run through various machine learning algorithms that can detect patterns in your data. Natural language processing is a twofold process. First, there's the data pre-processing, and then second, there's the algorithm development, both of which we will explore shortly. So checkpoint 1. Before we go any further, I'm going to just take a moment to pause and reflect on why all of this might be important to you. As a recap, there's a lot of tribal knowledge and accepted analysis within vulnerability tickets. By repurposing the information, process improvement can continue following automation. This process can then lessen human dependency and increase accuracy. You're also creating a nice transition from descriptive analytics to predictive analytics. Predicting severity levels is just a start. Any information that is consistently tracked within the vulnerability tickets is fair game to be analyzed. Project methodology. There are 3 main steps to this project. First, data pre-processing, which is the collection and preparation of data to run through machine learning algorithms. The end of this step will result in a final data set for step 2. Second, there's algorithm development. We're going to cover 5 common classification algorithms and how they help to detect patterns in the pre-processed dataset. The end of this step will result in observing the accuracy percentage of each algorithm and selecting the best one for the prediction task. Finally, we combine the dataset and selected algorithm to complete the prediction task. The end of this step will result in a right or wrong prediction from the test input. Okay, step 1, data preprocessing. The first thing you need is data. So normally you would already have this internally within whatever ticket repository your company uses. In this case, because we're using public data, the exercise of web scraping came in handy to gather the needed information. As an alternative, you can try finding a data set in a community repository like Kaggle. But for me, I wanted the experience of building and cleaning my own data set, so went the Python route. The other steps of pre-processing include removing dupes, replacing missing values with NaN, removing irrelevant words and using a stop word list to help with the removal, and adding a custom header. And just as a side note, a stop word list is basically a list of non-essential or no-impact words like pronouns, articles, prepositions, and conjunctions. Examples of these would be like a, and, the, your, are, and there. So it's basically words that offer no value for the prediction task. The final step was applying count vectorization to the natural language dataset to make it algorithm ready. This is basically running a script on the dataset to convert the text to numerical form. In this case, we are counting the frequency of pre-selected words mentioned in each CVE vulnerability description. All of the above changes were completed using Python. So here's a quick side-by-side comparison of the natural language dataset next to the count vectorized dataset. This is considered the completion of step 1, data preprocessing, of natural language processing. As mentioned, the dataset on the left includes the CVE ID, severity level, and most importantly, the vulnerability description in natural language. Upon count vectorization, the frequented words become the header, and the number of times they are mentioned in each vulnerability description are cataloged underneath. The severity level is still maintained because it is what the algorithms will use for the classification. The dataset is now ready to be added to the classification scripts. Okay, step 2 is algorithm development. So as mentioned before, the second step in natural language processing is algorithm development. The classification task is figuring out whether the frequency of certain words across multiple vulnerability descriptions are more likely to appear in one severity level over another, therefore allowing us to predict severity level for a discovered vulnerability. For this project, I opted to focus on 5 common classification algorithms. These are going to be helpers in detecting patterns in the dataset. For example, perhaps there is a certain word or cluster of words that are more frequented in, say, a vulnerability description. Specifically, a critical vulnerability description. Detecting this pattern would allow us to predict critical vulnerabilities in the future. Now, there are a lot more than 5 classification algorithms, but when you begin studying machine learning, without a doubt, these 5 will be encountered. So for the sake of an introductory level talk, we will use logistic regression, k-nearest neighbors, support vector machines, decision trees, and Gaussian naive Bayes. We are going to review these algorithms, and then we will make a selection based on results from the cleansed dataset. All right, so logistic regression is our first algorithm or model that we're going to be looking into. So this is considered a probability-driven model. logistic regression finds patterns in data sets by identifying the probability of an outcome. So in this case, the severity level. And this is based on the features that are present, which for us is going to be the list of our most frequented words. Out of the 5, this is considered the most straightforward model. The next is K nearest neighbor, or KNN. This one is a distance-based model. So when new data is introduced to the data set, the nearest data points are identified, and these are considered the neighbors. Using the value of K, you can adjust the perimeter of the neighborhood. And so although this is set to 3, in the actual script, you can actually adjust that value. So if you look at the image to the right, you can see there are 3 closest data points selected. Of these 3, the one with the shortest distance to the new data point will be selected. The new data point will then inherit the nearest neighbors class. Okay, so the second one is support vector machines, or SVM. So this one is a multidimensional model, and it's generally really helpful in classifying when you have a really complex data set. Its goal is to find the maximum margin distance in order to make the classification. So in this case, it's a 2-step process that happens iteratively until the maximum margin is detected. So for step 1, SVM generates multiple hyperplanes, which are basically lines that separate the data points into classes. In step 2, the model then picks the most optimal hyperplane, which is basically the one with the maximum margin. So the maximum margin tells us SVM has found the line that makes the clearest distinction between the 2 classes. The support vectors are simply data points that help the model accomplish classification. So in this case, that would be the blue circles and the red squares. So from personal experience, when I was running this data set for this project through this model took the longest to process. And so I'm thinking that occurred because based on this definition, probably finding like the maximum margin was quite difficult. So when I ran it through the script, I think it was almost like 2 hours in order to complete processing. All right, so up next we have decision trees. This is a flowchart model. So an interesting requirement with decision trees is the data set must be labeled. And this is known as supervised learning algorithm. So basically, like, you cannot have a data set that doesn't have labeling of features. So in our case, we have features. We're very distinctive of what we're looking for. If you had a data set that did not have that and you were doing more like exploratory data analysis, then this might not be the best algorithm for that particular project. But in this case, it was okay with decision trees. So the way it works is it classifies by starting at the top or trunk of a tree, and then it moves its way down with more specific questions to figure out similarities and differences within the data set. So in this case, you are classifying based on the most finite shared category. All right, last one, Gaussian naive Bayes. So this is another probability model. There are actually 3 types of naive Bayes models, but we're going to choose this one because, frankly, it's the simplest. This model is a derivative of the Bayes theorem. It means the probability of one event is determined based on the probability of a completed event. Gaussian classifies based on a normal distribution. If you look at the image, the model is calculating the probability of observing each data point based on the class. Okay, so next we'll talk about algorithm selection. So to figure out which algorithm to select for the prediction task, you run the cleansed dataset through a script that holds the libraries and classes for the selected algorithms. The output provides an accuracy percentage for each of the models. So that's the screenshot that's on the right. Based on the results, it's clear that support vector machine returns the highest accuracy percentage on the provided dataset. However, as I mentioned, this also takes the longest to process, so for the purpose of the demo, we're going to go ahead and use the second best, which is logistic regression. But I will still show you output on how the support vector machine fared. All right, second checkpoint. So as a recap, we know natural language processing is a two-step process of data pre-processing and algorithm development. We covered each of the classification algorithms that will be used to make an algorithm selection. And then next, we're going to walk through the prediction expectations and then input test data into a prediction script to observe the results of the prediction task. So this project is derivative of two other projects of similar nature. During the initial research, I wanted to get an idea of expectations and what the definition of success should be. If you look at the table to the right, there are important data points for both of the example projects, as well as the third one, which is mine. As you can see, there are both variances and overlap across all three projects. The general methodology of data pre-processing, feature extraction, again, that's the number of word frequencies, and algorithm development were also completed. The only difference is the number of vulnerabilities and features collected are much higher in Project 3. In thinking of what I was aiming for with this project, I wanted to gain an accuracy percentage that realistically could get presented for user buy-in. I knew if I had anything less than 90%, then the likelihood that users would feel confident in trying out this tool would not be very high. So fortunately, after an intensive journey of developing the size and the quality of the data set, the goal was reached with the logistic regression and the SVM models respectively. Next, we're going to talk about the impact of data to classification accuracy. The relationship is absolute. When I first started this project, I was gathering CVE data, including severity levels and vulnerability descriptions manually. I was hoping an even distribution across the 4 severity levels would result in adequate classification accuracy percentages. Unfortunately, the process was cumbersome and unsuccessful with such a small matrix. You can see as the dataset iterations progress and the number of vulnerabilities and features increase, the classification accuracy percentage increases in tandem. For example, if we follow the first row of this dataset, the relatively small number of vulnerabilities and features results in less than optimal accuracy percentages across the 4 algorithms. The other interesting part about this table is how mistakes in cleaning the dataset impact the accuracy results. This is evident in rows 4, 9, and 10. You can see either an errant column or row was left in the dataset before running the classification script, and that does impact the accuracy results. So here's a visual of the accuracy trend. This is evident with the linear trend line, which is in hot pink. And you can also see the random peak with dataset 4, where the column ID was left in. It should have been removed, but it basically created a false positive where I thought I had hit accuracy gold, but in reality, I just forgot to remove the ID column. So this is one lesson from this. Key takeaway is that, if you see your results being really, really good, even though the goal is to get as close to 1 or 100% as possible, if it doesn't make sense with the rest of the testing, then it's probably a good idea to check your data set. And in this case, just not removing a single column that had no value completely skewed the results. But aside from that, I mean, you can see that as the vulnerability numbers through web scraping increased, and also as the number of features increased, which is the frequency of words, as that count increased, there was just a steady trend up where the accuracy percentage also increased. So data matters. Okay. So a couple notes before we get to the demo. I did record the demo. I did it this morning because, frankly, I don't trust my coordination to do this live. But we're going to cover preparing the data set using a randomizer script. And then we're going to cover data pre-processing, which is going to be cleaning up of the data in both natural language and post-vectorization. Last, we're going to run the cleanse vectorized test input into the prediction script and observe our results. Okay, so movie time. Great. All right, so the first tab is just showing the classification accuracy. This is the percentage output that was in the screenshot. And that's just what it looks like once you run the script. All right, so this tab, we're going to create our natural language data set by randomly generating a list of CVEs. These are going to be pre-processed for the algorithm development. So this is not a requirement for this project, but it's just added for effect. Just to show that, if you randomly have a new CVE that's published and, your organization is aware of it, like, you're obviously not going to have that information right off the bat. Okay. All right, so yeah, that's data output. I did select 5 for the demo. You can do a lot more, and I have done a lot more, but again, since time is important, I went ahead and randomized 5. And then you can see the ID, severity level, and vulnerability description. That's all in natural language. Okay, so next we're going to open up the generated CSV. And yeah. Okay. So that's all the natural language data up front in the CSV. So the first thing I'm doing there is removing the header. We don't want to include that because then that's also going to get vectorized and it's going to skew our results. The other thing that I'm doing is I'm adding a placeholder column. So the count vectorization code, it will basically stop at that particular placeholder, and then it'll know to iterate to the next row. And so I add just this arbitrary term, and I just added starter column because that's where I want the iteration to start. And see. Okay. Okay, so the other thing I'm doing is I'm changing the file extension from CSV to text. Okay, next tab. So now we're going to run that text file through the count vectorizer script. So this script creates this useless first row of all zeros, and you do have to remove that. And so that's just what I'm showing here, is that it works, but for some reason it creates a first row of zeros that has to get removed. The other thing it's going to create is the column of IDs, the identifier. So that's another thing that gets removed as a part of the data processing. All right, so that's what it looks like when it's vectorized. You can see all of the features at the top. I think it's 592, and then you can see how the occurrence of each of these features is actually listed. And again, we're removing the first row, so that's all the zeros. We're going to remove that. That's not valuable. Okay, so as a side note, you can actually just do all of this through code, but I am showing the manual side of this for transparency. This is pretty much the stuff that has to happen before you can run this through your prediction script. Okay, yeah, and I think that is just removing the identifier. And then there's just one small formatting that's left before copying and pasting into the script. Okay, so that's the vectorization for all 5 CVEs. We're going to copy that, and then we're going to go to the script and we're going to paste it in. And again, we're doing this demo on logistic regression, which, if you can recall, it was roughly 90% accuracy. So we are looking for pretty good results. Okay, so now what we're going to do is we're going to run the script, and we are going to be able to see the actual prediction that's made for all 5 CVEs, and we're going to also see how it compares with the natural language output. Okay, so that is the prediction that's made on all 5 CVEs. It's read left to right, which is going to be, if you're looking back at the table, it's going to be top down. So critical, I think it's, yep, medium, low, critical, critical. And okay, so it looks like there's a 1-to-1 match on all of those. As a side note, I have done this with like a lot more test data, and it's not always 100%, but it's pretty close. I mean, even when I ran it with like 12 different test inputs, I still got 9 out of 12 using logistic regression, and that was about the same with SVM as well. It just takes so long to process, but yeah, it was pretty spot on with the accuracy percentage. All right. So this is how the other models fared. The only one that came back with a little bit of a hiccup was the Gaussian naive Bayes, but that was actually pretty expected. And still getting 4 out of 5 is pretty good, because I've run it again with a lot more test data, and there have been times when I only got like 3 right out of 12. But if you look at the accuracy percentage, it's relatively low, so it's not the best model to use for this project. But the other models, they're relatively close in accuracy percentage, and so the match was pretty spot on. And that was also the case when I ran it with a lot more test data. So that distribution is, it's pretty consistent. so a few key takeaways before we wrap things up. First, you have to keep processing time in mind for when the scripts run. I found as my data set grew, some of the models like SVM took upwards of 2 hours to complete. The second thing is there's a great benefit to this process improvement in comparison to just accepting the published severity level. The big benefit is that you can repurpose internal decision-making and tribal knowledge. These are things that are not always going to be integrated when you see like a newly published CVE. So that's very helpful. The third thing is there are two main assumptions this project makes. The first is the severity level. The severity levels in the current ticket repository are more or less accurate. And then the second assumption is that there's already an existing vulnerability ticketing process, and hopefully that process is somewhat automated. The fourth takeaway is the data set is really the most important part of this process. I mean, everything else, like, the code, basically the code, I mean, you can pretty much, find a lot of that information already on the Python website and in like numerous amounts of books and websites and whatnot. But if your data set isn't cleansed properly, it's just, you're not going to get the results that you want. And the last thing is, you don't need to be a mathematician or coding expert to get started. I mean, I'm obviously neither of those things, but a little knowledge can go a long way. So the whole point of this was really just finding another way to improve the process. That's it. Okay, so thank you. Thank you for attending my talk. Here are a few resources that helped me get started. Hopefully these will be helpful, but these are really like the main books and the websites that I reviewed in order to learn this stuff.
Hi, we had to kill all of the wireless mics because of interference. So if anybody has a question, please speak loudly, and if I can have the speaker just repeat the question into the mic before answering it, that would be great. Thank you.
Taking assets into account. So I think if you're thinking about prediction, you can definitely take assets into account if that is an item that is routinely collected in your vulnerability tickets. And so, once a CV gets published, if it's relevant to your organization, and you end up finding impacted assets, and that information is consistently collected, then you have a pattern. And once you have a pattern, then you could utilize something like this. And what it would really do for you is just, if there was something similar that came up again, or maybe you knew that, basically if there's something similar that comes up again, you can utilize this historical knowledge that's already in your vulnerability tickets in order to predict things like what are the assets might be impacted by this, or like who are the owners of these assets, or where's the root cause. So it really comes down to what you're consistently collecting, and then that's where these machine learning models can really help you out to make whatever prediction you want. So severity level is just one type of prediction you can make. But the real question is, you'd have to look at your tickets and say, hey, what are we doing consistently? What's the formatting like? If I put everything in a CSV in a table, how much of that information is like consistently collected? And when you have that, then you can repurpose that information to make predictions.
I think that what she's asking, please correct me if I'm wrong, I think what findings was WebKit on iOS. If I don't have any iOS in my system, but it's critical, then the severity is probably low since I have them. That's, I think, what you were saying.
That's the kind of use case I'd like to
Right.
be able to address using.
So if you applied another column of, do I have what's applicable to this finding, then that gives usable output.
Yeah, you can.
Yeah, I think so, but I also think she answered the question, which is it just depends what data I've collected. So if I have the historical information about which assets have been impacted by a given type of vulnerability, I'll be able to derive those predictions.
Yeah, I think it's also, yeah, that's exactly correct. And then if there is a new vulnerability that's introduced that your organization has not encountered yet, the process of like feature extraction that we discussed, which is like the most frequented words, that could also give you insight. Like as long as that, you can actually adjust the number of features that you include in your data set, but if you wanted to add other things and then you wanted to count if there's like how many times iOS is mentioned in like all of the vulnerability tickets, and then that would help you to find like the nearest classification, you know, that's another adjustment you can make. Kind of, yeah.
So on the ones that were not fit, so let's take SDN, right, that has accuracy percent and 5%. So if you look into the variance of that 10% that wasn't matched,
Yeah.
and is it a very big variance? Like, would they have a critical that was rated as a low, or are they close?
Oh, that's a good question. Yeah, when I did testing, it was very close. So most of the ones, okay, so I did testing multiple times, and I didn't get any of the critical or highs incorrect. What I did get incorrect were medium and lows. And so whenever there was like supposed to be a medium, for some reason we would come back as a low, or if it was a low, vice versa. And I should have included screenshots of that, and I didn't. But it's the variation is not extreme. It's not like if you see low, then you know it's supposed to be a critical. I did not see that in any of the testing, but it's a possibility. You know what I mean, if you share the terminology, yeah.
I'm just concerned that you miss a critical in that 10%, however slight, right? Even if it's 5%, then you miss a critical because of the and if you do that on the model, you would have discounted that critical because it was because of the right. Now
Yep.
That would be a miss.
Yeah, that would be a huge issue.
Actually,
Yeah.
Did you include any information?
Huh?
Did you include any information? Look, I've done a lot of pen testing.
Yes, I did actually.
Okay.
Yeah, I included every.
A lot from what you're talking about. Informational being critical, being chained together, especially as turned into a critical, is not very uncommon. Were you able to account for that?
I don't think that was included into it. I think it's just mainly like you're looking at the most common occurrences of words, and the assumption that you're making is that there are certain words that are more commonly reported in like a critical vulnerability versus an informational or a low. But it does not encounter like changes. Like if there's, something happens and you're like, oh, actually we have to like bump this up to a critical. It doesn't include that, except for the fact that if you have already experienced that multiple times and maybe there's something consistently tracked in the vulnerability tickets, then perhaps like those keywords would pop up, and that could help you to consider like, that pattern.
Like an example, NFS is something that SS doesn't do well. It's a known, it doesn't do well. So it gets put as an informational quite often. The pen tester going in will take that NFS attack, they'll get in and then find all kinds of things that make it critical. So, that's an example of where
It's kind of an overarching problem that you're bringing in though with the vulnerability.
Yeah.
System as a whole, which I think is
Well, right.
orthogonal to the process here. I mean, important, but orthogonal to the process.
It's also, this process is bespoke to your organization. So it would also include, if something like that ever occurred. And so the whole point of this is like you're repurposing information and decision making that applies to your organization versus just like arbitrary, like, generic severity distribution. And so if you have like a history of like, NFS showing up and then it getting bumped up after a pen test, and that is tracked within vulnerability tickets, and that could very well be something that comes up and offers you a more accurate prediction. But if it's never been there and that terminology is not present, then yeah, I mean, that's where that deviation would occur. So definitely correct.
So, I didn't see a feedback cycle here. So if I run this and it matches like 90% match, now I have predictability score for just one cycle. If I then apply on this one first cycle, if I then apply my knowledge or the team's knowledge and go, these are real critical, these are not because of environmental factors. On the next one, so every one should be able to get better and better
Right.
into predicting whether certain ones, and you might even feedback into the model, whether a certain critical really, like for example, if I have no iOS, like over a few cycles, the model should say it's a critical, but previous learnings have shown that it is not critical because of iOS, lack of iOS. And the machine doesn't know that, doesn't have iOS. The fact that the model just knows that previous.
Yeah, the previous. Yeah.
It was critical but marked down as low. And so when it gets to a spot where you say, because of those learnings from before, now this is a low. And how would you integrate that into this kind of a feedback cycle?
So my response is probably a bit junior, but if I were to discover new information, then I would probably restart the collection of features, the feature extraction, and then rebuild the header, rebuild the number of headers, because at that point there might be new terminology that comes up. Yeah, and then I would rerun the natural language through it again, and then vectorize it, and then see if there's improved results. So that's probably how I would do it. It's a long process. Yeah, you would definitely have to.
I'm just wondering
Yeah.
how does it keep that decision? So let's say over a period of 12 months, every month it goes through the cycle. How does that, it's December, how does it keep all the decisions that it's made from the previous 7 months? And then to be able to make that decision on the 12 months.
I'm guessing logs.
Okay.
Yeah, I would say logs.
I guess,
Yeah.
the whole thing about this is trying to reduce human intervention,
Yeah.
right? And so today, you need a team of 20 analysts.
Yeah.
Each one of these. In 6 months, I only want 2 people to look at this. With the rest, doesn't mean that the model will go down, but just that the machine learning model is able to cut out the work of those other 10 or other 18 folks.
I'm sorry, could you repeat that, please? I didn't quite understand.
So my use case in my head is that right now I have an analyst team of 20 people looking at 1,000 vulnerabilities.
Yes.
Is it possible to use this so that in 6 months or 12 months, I would only need half the number of analysts with the machine model taking
Oh,
over
yeah,
the other half?
yeah. That's the goal. Yeah, that's definitely the goal, because then you'd have all this historical knowledge and you're running it through this over and over again. Yeah, absolutely. There's like that compounding that's occurring. Yep.
The machine, at that 12-month level, the machine model is making that decision.
Yep.
Instead of analysts going, that's an iOS one.
Yep.
I don't have iOS.
Yeah.
The machine is going, that's an iOS one. You might not know it's an iOS one.
Yep.
It'd actually be taking the 10% that's off and continually running that for until it figures it out, right? Yeah. I mean, that's a good model. Keep iterating on that 10%. Isn't that what you're thinking? So, okay. So that's brainstorming on. Because you can identify that 10%, right? Or 8%. It's not the 10%, it's really the 90% because I haven't figured out the feedback on this, right? So when you do run this, it does issue. So you
that this new model does match 90% of the criticality
Yeah.
and the severities, but there's no, at this point on the first cycle, there's no tribal knowledge to go in and say, are those really critical? It's just the machine is matching between a CV score that's
there is tribal knowledge at this point. So for this project, I had to use public data, and that's why it kind of looks like public data. But the theory is that you would be using your own vulnerability tickets, and those tickets within your org would have tribal knowledge. And as a result, the features that are extracted would be completely like they would be whatever your organization uses. So if you have like some special term for critical, or you have some special term for something else, and that's like consistently tracked, then that would become a data feature, and then you would count the occurrences of that. And hopefully that would align with the common severity level that's been detected. Does that kind of make sense? Yeah. Okay.
It kind of goes towards what you're saying about
Yeah.
even if it's a critical, that the CVE score is critical, but in your environment, it's a no.
Exactly.
Yeah.
Yeah.
The machine will be able to produce that eventually. But that's where the tribal knowledge comes from. Thank you.
Thank you. Thank you. Thanks.
Are you planning to open source the website you're using?
Yes, there's more things I want to add to it though, because it's still relatively elementary. So I have this whole backlog, but for this presentation I had to cut off and just post what I had. But if I do post, because it's data science related, I'll probably put it on Kaggle. And then it'll just, all the code and everything will be, within Jupyter Notebooks, and the data set would be available as well. It's a pretty big data set. I web scraped over 150,000 CVEs, and, the other published works were, definitely less than that. I think I don't remember, but it was almost half. So it's a lot that I was able to work with, and I think that is really the reason why the accuracy percentage, went up. Yeah. Yeah. Thanks for attending though, and thanks for all the questions.